Welcome to AlgoStock. Today, we're diving deep into decision trees, a powerful tool that helps us uncover hidden patterns in data. We'll explore everything from building a tree, pruning it, and avoiding common pitfalls to understanding its pros and cons. So, get ready to follow the clues as we solve the mystery with decision trees. Imagine you're a detective solving a mysterious case. Each observation you gather is a clue, and each feature, like temperature, day, or event, is a suspect in the investigation. But the clues don't form a simple path, they're scattered, and each suspect could lead you in different directions. So instead of following a straight line, you decide to interrogate each suspect one by one, making decisions based on what each suspect reveals. This is exactly how a decision tree works. It splits the data based on the most suspicious feature, narrowing down the suspects at each step. Like a detective who breaks down a case into smaller leads, a decision tree breaks down data until it can make a confident prediction. Why do we need decision tree regressors? Imagine you have a traditional detective, a detective who can only follow a straight path. They do great when all the clues line up neatly, leading directly to a single conclusion. This is like using a traditional model, such as linear regression, which assumes that all clues have a simple, straight-line relationship to the outcome. But what if the case is more complicated? What if the clues twist and turn, and different suspects become more suspicious at different times? That's where our clever detective, the decision tree regressor, comes into play. This detective doesn't rely on a single path. Instead, they carefully examine each clue's behavior, solving mysteries involving complex, non-linear relationships. Take, for example, investigating sales at a lemonade stand. Our suspects are the temperature, the day of the week, and special events. But the link between these suspects and the sales isn't straightforward. Sales soar on weekends when it's hot and there's a local event. But they drop if it's cool even on weekends. On weekends with moderate temperatures, sales still climb if there's an event but remain steady without one. On weekdays, sales are usually lower, but they can spike if an event happens, even when it's hot outside. What is decision tree? Picture it as the detective's decision-making flowchart. Each decision point, or node, is like an interrogation with the suspect, a key feature in our investigation. As we move down the branches, we're gathering more information, narrowing down the possibilities one clue at a time. Eventually, we reach an endpoint, called a leaf, where our detective has gathered enough clues to make a prediction. It's like concluding the case. After considering all the evidence, a decision is reached. The decision tree is built by picking out the most suspicious suspects first, examining each one in detail, and gradually focusing on the most relevant information until a prediction is confidently made. For example, if there is not event, and temperature is less than or equal to 36.26 degrees Celsius, but greater than 28.65 degrees Celsius, decision tree predicts the sales to be 89.07. How it works, step by step. Let's start simple, focusing on just one suspect in our investigation. Temperature. We want to see how this suspect alone might affect lemonade sales. Imagine our detective is only asking one question: what is the temperature? First, we line up all the temperatures in our data from the coolest to the hottest days. Then, we identify decision points by looking at the gaps between each temperature. We take the average, or middle value, between two consecutive temperatures and treat it as a potential split. Each of these split points is a moment where the behavior of our data might change, where the temperature could start to make a noticeable difference in sales. By pinpointing the best split points, we can unravel how temperature alone guides our predictions, whether it's a cool day or a blazing hot one. Each split gives us more insight into what drives those lemonade sales. Now, our detective needs to decide the best split point. How do they make that decision? They look at every potential split and calculate something called the weighted mean squared error. Here's how it works. Each potential split divides the clues, the data, into two groups, a left group and a right group. For each group, the detective calculates the mean squared error, or MSE. This MSE measures how well the detective's prediction matches the clues in each group. To make the prediction, the detective uses the average value of each group. In other words, they assume that every clue in the group can be summarized by the group's average. But the detective doesn't stop there. They need to consider how many clues are in each group. So, they calculate the weighted MSE, which takes into account the number of clues in the left and right groups. Here's the formula they use. To truly understand our detectives' method, let's follow them as they solve for a single split. Imagine they've picked a potential split point, dividing the temperature data into two groups, one cooler and one warmer. Now, the detective wants to see if this split is meaningful. How well does it help predict lemonade sales? First, they calculate the prediction error for each group. To do this, they use the group's average as the prediction, like a detective assuming all clues in that group point to the same result. The detective calculates how far off each clue is from the group's prediction, squaring the difference and to avoid any negative numbers. Then, they calculate the average error in each group, the mean squared error MSE. These MSE values tell the detective how accurate their predictions are for the cooler group and the warmer group. But not all groups are equal in size. To get a fair evaluation, the detective considers the number of clues in each group. They calculate a weighted MSE by balancing the errors based on how many clues fell into the cooler group versus the warmer group. By balancing the errors of both groups, the detective is searching for the split that results in the lowest weighted MSE. This split isn't just about reducing prediction errors. It's about finding the most meaningful way to divide the data while taking every clue into account. To make the process clearer, imagine we plot the weighted MSE for each potential split. As we move from one possible split to another, the weighted MSE might go up or down depending on how well that split captures the hidden patterns. The detective carefully evaluates each of these values, calculating the weighted MSE for every potential split. The goal? To pinpoint the split that gives the smallest weighted MSE, meaning it does the best job of predicting lemonade sales with the least error. This is how the detective narrows down the most informative split, step by step, ensuring no clue is overlooked in the analysis. Now that we've found our first split, our detective is ready to show us the first step in their decision-making process. Imagine our data as a tree split right down the middle based on the chosen temperature point. In the left branch, we have 12 samples out of 20 with an average value of 97.983. This means that if a day falls on this side of the split, our detective predicts a sale around 97.983. In the right branch, there are 8 remaining samples, averaging to 130.045. So, on days that land here, the prediction would be closer to 130.045 based on the temperature. But the investigation doesn't stop here. Now, the detective zooms in on the left group, those 12 samples. To the detective, this left group is like a fresh case, a new dataset to solve. They'll apply the same method, searching for the best split just as they did before. The only difference is that now, these 12 samples become the detective's entire dataset at the current depth. This is what our tree would now look like. In similar fashion, detective now splits the right node. Detective keeps on following to grow the tree, and ultimately this is what the entire tree looks like. At this point, our detective has gathered enough information. But if they keep splitting, they might create a story that fits the training clues too perfectly, leading to overfitting, where the model struggles with new data. To avoid this, the detective sets boundaries, a maximum depth of 3 splits, and a minimum of 7 clues to justify a new split. This keeps the investigation focused and prevents unnecessary complexity, ensuring the detective builds a clear and reliable story without getting lost in the details. Note, though this cell has 2 samples and thus the ability to split further, detective doesn't allow this since the minimum samples required to split is set as 7. And, though this cell has samples more than 7, detective doesn't allow it to split further since the maximum depth allowed for the tree is 3. Now, let's bring in our other suspects, event and day. This time, the detective isn't just looking at temperature. They're investigating all 3 suspects to find the best first split. Instead of focusing on a single clue, the detective searches through every feature, temperature, event, and day, calculating the weighted MSE for each possible split. Since event and day are binary features, they only have one possible split each, making it easier to evaluate them. The detective then compares the results from all potential splits across all suspects. Whichever split results in the lowest weighted MSE will be the first node of our decision tree. Since splitting based on event is giving us the lowest weighted MSE, this suspect will be used to split the data first. As the investigation deepens, the detective continues to examine all 3 suspects, temperature, event, and day at each level of the tree. However, the detective now only considers the clues currently available at each node. With fewer clues to work with as the tree branches out, the detective calculates the weighted MSE for each feature, using the data present in that specific branch. Pitfalls and misconceptions. Overfitting. If the detective interrogates every suspect too deeply, it can end up with a story that fits the clues perfectly but is just too complicated to solve new cases. This is called overfitting. Misconception. Bigger trees are better. A deeper tree isn't always better. Sometimes, a simpler story helps the detective solve new cases more effectively. Just like a detective sometimes ignores unimportant clues to keep the case simple, pruning cuts off branches that don't improve the model to avoid overfitting. Pros and cons. Decision trees come with their own set of strengths and weaknesses, just like any detective's toolkit. Here are the key pros and cons to keep in mind. Pros. They are easy for our detective to interpret and visualize, making it straightforward to understand the decision-making process. They can capture complex relationships between suspects, handling interactions that simpler models might miss. No need to worrying about feature scaling. The detective can analyze clues in their raw form. Decision trees are less sensitive to outliers compared to linear regression, keeping the investigation stable even if a few clues are unusual. They work well with both categorical and numerical features, and can even handle missing data without much trouble. Cons. However, the detective can fall into the trap of overfitting if they follow every clue too closely, creating a model that's overly tailored to the training data. They are also sensitive to small changes in the clues. Tiny variations in the data can change the tree structure. Decision trees don't always perform well with very few clues. They need enough data to make accurate splits. Without proper pruning or regularization, the investigation can get too detailed, making the model unnecessarily complex. If the dataset is imbalanced, the tree can be biased, leading the detective astray. And as the dataset grows, so does the training time, making it more challenging to handle very large datasets. Decision tree regressors are like detectives who follow complex trails of clues, interrogating each suspect to find the hidden story in the data. They're powerful tools for making predictions when simple linear models fail to solve the case. Just like a detective, they need to be careful not to get lost in unnecessary details. Would you like to explore more about how to bring in a team of detectives to solve even tougher cases using random forests? Stay tuned for the next chapter.